Okay, so today we'll be learning about Newton's law of universal gravitation. So we're going to start the class with a focus question, and that will be, how do we determine the mass on Earth? Sorry, the mass of Earth. Okay, so the problem with finding the mass of Earth is you can't really put Earth on a scale. So the question is, how do we do this? So the first step in doing that is we have to find out what the acceleration of gravity is, the constant, the local constant. So I would ask the class to recall the kinematics unit, which was the unit before this. So the formula we're going to be using for this is d, which is displacement, is equal to the initial velocity times time plus 1/2 the acceleration and then the time squared. So here what we're trying to find is this acceleration. So if I had a mass and I dropped it from in the air, the initial velocity would be 0, correct? So that means that this entire part here is equal to 0. So now all we're left with is the 1/2 at squared. Okay? So by manipulating this formula, you're going to end up with A is equal to 2d divided by t squared. Does that make sense? Okay, so your distance, let's say we dropped it from 1 meter, okay? And actually how I would do this is I would have an activity with the class where I drop something from a certain height and I would have some of the students with stopwatches, but it doesn't really make sense for this. So we'd end up with some times and we discuss those times and how we probably wouldn't get the same acceleration as the proper acceleration, so talk about that. But the acceleration that we are supposed to get is 9.81 meters per second squared. Okay? So, and this right here, this is a local constant. So it's the constant here in Edmonton. It actually differs a little bit as you go to the equator and the poles. But this is the constant we're going to be using for this class. So this will be provided for you on your formula sheets, but this is, we're actually going to call this G. So anytime you see G, that's going to be your acceleration due to gravity, which is 9.81 meters per second squared. Okay, so next I'm going to show you what the Newton's universal law of gravitation. Okay? So for this is a force. And this formula, or this law, actually states that any two objects, anything in the universe, have gravitational attraction to each other. Okay? So it doesn't matter what they are, big or small, everything is brought together through gravity. Okay? So the formula for that is G equals mass 1 times mass 2 over, and the R, that's the distance between the two objects. Okay? Whoops. Okay, so this G, this is a constant, and this is a universal constant. So this G is equal to 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. And this is another one of those things that you won't have to memorize. This will be provided on formula sheet, okay? So this is the universal gravitational constant, and this is the same anywhere in the universe. Okay. So I'm gonna do an example. And the example is the gravitational force between two people. Okay, so we have one person, let's say their mass is 75 kilograms. And we have a second person, and their mass is 90 kilograms. So as I would have said before this lecture, anytime you're doing a force problem, I want you to draw a diagram, okay? So just a really quick sketch, doesn't have to be anything super intense. I'm just going to use stick people. And these, sorry, I forgot to include, these people are a distance of 1 meter away. Okay, so there's a force here, and there's a force there. And the distance is 1 meter. Okay. So, for this problem, we're going to use Newton's law of universal gravitation. So, Fg is equal to G times, and we're going to use the first mass here, 75 kilograms, the second mass, 90 kilograms, all divided by the distance, which is 1 meter squared. Everyone following that? Okay. So the answer that you would get if you did the calculation would be Fg is equal to, sorry I have to consult my notes here, 4.50 times 10 to the negative 7 newtons. Okay, so you can see that that's actually a really small number, so there's not much. Unless you get into the really big masses like planets and stars, you're not going to have a huge gravitational force, but it is still there. Okay, so there's always a gravitational force between two objects. All right. So now, to address our focus problem for the day, which is how you find the mass of Earth, we're going to be using everything that we've learned today. So we're going to use the acceleration constant, local constant, and we're going to use Newton's law of universal gravitation together. All right, so first of all, recall from last class, we learned that F equals ma. And that's Newton's second law. Okay? So for this problem, we're going to use the acceleration of g. So it's going to be F equals mg. Okay? And then the second equation is Newton's law of universal gravitation, g m1 m2 over r squared. All right. And this is a gravitational force. So as you can see, we have a force of gravity here and a force of gravity here. So what you can do is you can actually combine the equations. You can replace this Fg over here in Newton's law of universal gravitation with this. Does that make sense? Okay. So what you're going to end up with is mg is equal to g m1 m2 over r squared. Okay. So this mass here, for this part here, this is the force of gravity on an object that is on Earth. Okay? So just like we did in the activity at the beginning of class, where we dropped an object from a certain height, that object had a mass. So that mass is this mass. And it's also this mass. They have the same mass. Or they're both m1s. So what you can do is you can actually cancel those out. And that works by dividing both sides by m1 and they cancel each other out. Okay? So you're actually going to be left with g, so the acceleration of gravity, times g m2 divided by r squared. Okay. So this m2, that's what we're trying to find. That's the mass of Earth. All right. So we obviously, the first thing we have to do here is we have to get this mass by itself. So again, we're going to manipulate the formulas. And we're going to end up with, can everyone see that low? Okay, perfect. So when you manipulate the formula, you'll get your m2 is equal to the acceleration of gravity times the distance over g. Okay. So this is what we're trying to find. This is what we've already found, 9.81 meters per second squared. This is a constant. This r squared is the only thing that we haven't found out yet. And that right there, because the Earth, most of the mass of the Earth is in its core. Okay? So this r squared is actually going to be the radius of the Earth. All right? So, and the radius of the Earth, and I'll write RE, is equal to 6.4 times 10 to the 6 meters. Okay? And you have to be careful to use meters, because that's the unit that you have to use. If you look up this value on the internet, they'll give it to you in kilometers, so you have to convert it to meters. Okay? So now we have everything we need to figure out the mass, and you can just plug all that in, and you'll end up with the m2 is equal to 6.02 times 10 to the power 24 kilograms. Okay. And again, if you look this value up on the internet, it would be slightly different. What do you think would cause that value to, what do you think caused our value to be slightly different from the actual value?
Say the G.
Sorry?
The G?
Sorry?
Like the acceleration due to gravity, that might change like tiny bit.
Yeah,
Tiny.
for sure, yeah. Because it's different from around the globe. How about, do you think that we might have rounded off some of our numbers quite a bit? Yeah. And when you're dealing with big numbers like this, like 10 to the power of 24, it is important that you try to round off the least you can. Okay? Okay, that's the end of my lecture.